Okay, this blue color is a vector field, no? As you know, F1, F2, and so on. Ese variable, no? Ese vector field que no consta ese variable. Now, if you perform at any point the dot product, so the dot product is a vector field in any point, dot product, the dr, and by the way, let me recall who is dr. Dr, this is vector field, and this is the vector also. And this is f dot product tangent vector, unit tangent vector, ds. And ds, remember, is infinitesimal at length of the curve. And of course, you integration this to any point. Okay? Integration is the same meaning we study anytime is Riemann sum. Summation, any dot product, and any infinity point in the specific curve you want, and this is a circulation. And the specific example, of course, the vector field, not necessarily like that. This is circulation. Circulation. Mathematical thing. Mathematical operation. Now, in the physics, I try to understand the physics meaning. Okay. And the specific example, que the vector field is a force. And Newton, obviously, the circulation integral represents the world. This is Newton. This is meter. This displacement. A Newton meter is a joule. This idea is clear. This idea is clear. This idea is clear, Alejandro. Dice Alejandro. Ahora, now, we study today Newton, que es a flux integral. This is always confusing. The students don't understand very well flux integral. Suppose we have again a curve C. And suppose again we have different points. And the flux, so this new word, flux, is the how much vector field passing through the curve C. So it's okay. This is very, very complicated to understand this, but I try. Okay, flux is the amount of something. Okay, this something depending of the vector field. No? Okay, maybe is water because it's the flow of water. So it's important that you understand two words: flux and flow. I want to explain it now. But flux is the amount of something. Maybe it's water, maybe it's electric field, maybe it's whatever you want, passing through the surface. Es something. Maybe banana. Suppose que the banana passing through the display of the Publix es a flow. It's a flux. Entonces, flux is mathematical. Similar to the circulation, es mathematical too. So let me try to understand. Okay, we have in this point a vector field. Again, suppose this vector field, suppose this vector field, suppose this vector field. In any position, depending on the vector field, you know. Now, in order to find the flux integral, you determine the normal vector, not the tangent vector. Normal vector is a vector, suppose que it's like that. This is normal vector que we represent guy like M. I don't know why in this case represent in low case in any book. Normal vector. Entonces you say, bueno, professor, pero what is the reason que you put in this orientation? Bueno, it's true. maybe we are doing in opposite orientation, like that. That depending what is your goal. So your goal is determine the flux inside, it's like get inside the surface, or no, the flux can go outside, get out, outside. Entonces now, similar idea, we apply in any point the dot product between the vector field F multiplication by, o sea, dot product, no multiplication, dot product, the combination normal vector ds. Okay, there are no specific name for this. For example, TDS is DR. However, MDS is no name. But basically, the idea is clear. When you perform the dot product and you integration, this is the magic idea. Is the Riemann zone, you get the flux integral. Okay, and the flux depending of, in my opinion, depending of three things. The flux depending of three things. The flux depending of flux depending of three things. Number one, of the vector field, because the vector field is a source or sink, depending on the direction. No? It's the strangeness of the flux. Depending the surface psi. See, I want to find the surface in one big surface. The flux is a big number. No, see, it's a small surface. It's not big number. And the orientation. I want to explain everything in detail now. Okay, all right, now let's come back again to the unique. And see, I want to find physical meaning of the flux. I need to similar the thing I did in the circulation que was a work. No? In this case, I suppose that the vector field F, no, it's not force, it's velocity. The unit of the velocity is meter per second. No? Okay. And when you multiplication in this formula, meter per second, and this, que es meter square, because it's area, surface, you have meter cubic per second. And this is flow. So flow is the flux, but under the consideration que the vector field is velocity. Si the vector field is no velocity, it's another thing, acceleration, momento, linear momento, I don't know, another thing. And then, entonces now is flux. The flux is a more generic word to define one kind of the integral over the vector field. Like a circulation is more general than the particular example in which the vector field we are talking about force, entonces es a word. Okay. Okay. Ahora, Professor, I don't understand anything because you are explaining a curve, no surface. Where is this surface? Well, okay. The problem is that we are working in 2 dimensions. So this problem is 2 dimensions. I promise that not today, but this week, we are doing in 3 dimensions. Okay? Because to start doing in 3 dimensions, we need another tools that you don't know now. That to explain the flux in 3D is more complicated. But today I want to try to explain the flux in 2 dimensions. Entonces, bueno, no, pero entonces I don't understand very well what is the surface. Well, the surface is formed by the curve, this curve, But if you want to eliminate one dimension in the problem, you suppose that another dimension gets hidden. Okay, I suppose, look, I try to see the picture in 3D. Okay, suppose now that we have surface. And this surface is formed by this curve, exactly this curve I did before, huh? Here. But another dimension that you don't see gets perpendicular to the whiteboard is equal to 1. So this area surface is multiplication, this r length multiplication by 1, and this is the area. Okay, in the two-dimension problem, I suppose that the dimension that you don't see is 1. And remember, this is 1 is magic, no? Because when you assume 1, we discover that the double integral, the normal is a volume, you represent like an area, and you know that when the one dimension is 1, and triple integral, that normally the interpretation is a mass, become like a volume, and the line integral in a scalar function, with the scalar integrand function, remember when there is 1, this line integral becomes like a r length formula. Entonces, tu consideration que one dimension is 1 is useful to reduce the dimension for the our problem. No? Okay, so now, do you understand where I come from surface at least? And what about orientation? Orientation depending on your goal. So you want to get the flux que go inside, get in, or no, or get out. So now you define in your problem according to your goal and what is the orientation. No? So you determine the normal vector. Okay, let me. I explain the orientation because sometimes we have flux, positive flux, negative flux, or zero flux. So to explain this, I bring something out. Let me see. I bring this picture. Bring this picture. I don't know what happened with this. Okay, come on. Click. Okay, come on. What's going on? I got it. Okay, let me make a zoom to see more clear. Okay, in this picture, it actually is an example of physics. Not mathematics, it is physics because the vector field is magnetic field. When you see capital B, it's because capital B is a magnetic field. No, but a magnetic field is one particular example of the vector field. So, for example, you can see that in this surface, the normal vector is, you assume, is in this direction. And I want to compute in this the flux can go out this surface, no? And this case maximum because the vector field and the normal vector are parallel. Wow, nice. Entonces, when you perform the dot product, it's maximum. However, see, I want to compute the flux under the consideration that the normal vector is in this direction because I want to compute the flux can get inside, and then it's completely opposite sign. It's maximum, but it's negative. Okay. And now the flux is 0, see, it's perpendicular. Okay, see the flux. See the vector field, sorry, es perpendicular to the normal vector, entonces the flux es 0 porque el dot product es 0, ¿no? Entonces one specific intermediate angle, you can see que es the classical formula que you see in physics, que es vector field In this case, multiplication not by displacement is area of the surface cosine theta, que es the angle deformment between this. Okay. At the beginning, the student don't understand very well. But suppose you have a waterfall, 3 waterfall. But you have a container, no? You put a container here in that position. It's obvious that you get the majority of water inside, no? A lot of water. However, if you put the container in this position, then you never get water inside. Okay, the reason is because my surface cannot necessarily physical surface. In this case, it's air, but the normal vector is in this direction, and the vector field is in this direction. So it's perpendicular, no water. Ah, bueno, no, you say, bueno, professor, the water hit that and it split. Maybe, yeah, but you neglect this effect. Okay? So this is flux is positive. This flux is 0. And to create the effect of the flux, well, I don't know, negative is when they go outside, you know, or in opposite direction. You know? Suppose que here, and well, I don't know, it's the opposite direction. You get the idea for the flux or no? You get the idea? Do you understand the thing? I try to start working. Okay. I bring one more resource to explain this, que es the animation que I create. No, I do not create. I copy. I copy in internet. No? I copy one animation. Okay, look. Okay, share the screen to show you the animation in Geogebra. Switching to animation, Geogebra animation. Okay, well, do you see or no? Do you see the animation? In this animation, I see the vector field. Okay, look, this is the particle. No particle. This is the vector field. We have surface. Okay. Now the particle simulate the flow of something. Okay. Now we compute the flux. And the flux, depending the orientation, explain that. And the orientation, maybe I change here in the angle. Look, the angle of the surface. And you see how change the flux. Even when it's 90 degrees, no flux. Well, at least first approach is understandable or no. So my goal is no, can you learn how we compute the flux? No. You understand what is that, no? Or no? Because it's a chain, no? Okay, you finish calculus 3. Yes. And you see, I never understand what the flux. Okay. Now let's move on to the computation there. How we compute the flux. Integral. So we have 2 kinds of integral. The circulation and the flux integral. Okay, let me try to share this, the webware. There you go. Okay, so far, the only thing I understand is that the flux integral, okay, to compute the flux integral, we are doing the line integral on the curve C of the one vector field, but in this case you prefer the dot product with the normal vector. So we emphasize the idea for the normal vector. So ds is a scalar, guys. This is the normal vector of the curve, and this is the vector field. Entonces now I know que tangent vector ds, oh, it's easy, es dx dy. But I have no idea what is m ds. I try to find out the formula, no? However, after I want to use intuition. But okay, formula first. Okay, to find the formula, in my opinion, I have, for example, I come back to see the problem in 3 dimensions. Suppose this is a curve, C. In one specific point, we have, for example, suppose a tangent vector. So I suppose that I like this orientation. The normal vector look like, I don't know exactly what is the equation for this, look like that. But it's perpendicular. This is, the idea is clear. This is 90 degrees here. Entonces now, in order to find the formula for the normal vector, I suppose the problem in 3D, in 3D we have one vector here. Okay, obviously, si you suppose que es univector to indicate direction, is the univector K. Okay, the univector K, everyone know que es 0, 0, 1. Okay, entonces look at the picture. I saw that the normal vector, maybe we can find using the cross product in between tangent vector cross product K. Makes sense, right? Remember the right hand rule? My finger point to the direction of the tangent vector. I rotate my finger to touch the arrow of the K vector, and you get in my thumb the normal vector. Okay, I suppose it works. However, to find the cross product, I need the vector in 3 dimensions, no in 2 dimensions. Okay, so I call the vector dr. Okay, the vector dr is in the same direction for the tangent, no? Is the vector dx. Well, I have here. I don't need to copy. I have here. This vector is dr. This vector is dr. I copy dx, dy, and the other component is 0. We have no component. But unfortunately, to apply the cross product, we need the problem in 3 dimensions. And the k vector is a vector 0, 0, 1. And you are doing this famous cross product. And the answer is, I skip that part because this is too easy for us. Okay, they perform the cross product determinant. We are boring to do this 3,000 times. The answer is dy, dx, c. Okay, entonces si I omit the dimension, the third dimension, we discover que the normal vector ds is equal dy, dx. Espérate, I make a mistake here. Es minor here. It's over the minor. Dx. And this is super logical. Because you have 2 vectors. Look, you have 2 vectors. Suppose a comma b, 1 vector. And you want to find one orthogonal vector to this. You are doing 2 things. You interchange a and b. You put b here and a, and change the sign at least in 1. Maybe the second, like I did that, or the third, depending on the orientation that you want. When you perform the dot product in between these two vectors, es 0. The answer is 0. Entonces, this is the idea. Okay? Entonces, super easy. Because you are familiar with the circulation integral. The circulation integral is f dr. And f dr is, suppose, vector field in 2 dimensional, pq, dot product, and dr is dx. dy, no? I did before in the last class. Now it's the integral p dx plus q dy. Boom! It's a formula when you have no parametrization. Oh yeah! Or natural parametrization or specific parametrization. The parametrization depends on the curve. In what way you consider it is countable, better to do the parametrization. However, in the flux integral, you have this new situation, no problem m ds. Well, we have a vector field again, p, q. Dot product, and now this vector I prove mathematically is dy, minus dx. Okay, and when you perform the dot product, we have p dy minus q dx. Wow! And this is the formula for the flux integral, and this is the formula for the circulation integral. End the story. Super easy. Pretty easy. Do you understand very well or no? Everyone follow me? Confusing? Hey, answer me. I teach you the class is empty, or I have a student with me? No confusion. Okay. So now, of course, we see example to understand that from today you are aware that we have two kinds of the line integral over the vector field. One is circulation, another is flux. And you understand a little bit. I promise a little by little you understand much better the flux idea. Okay. Entonces, example one to understand. Remember, important in mathematics is teacher explain definitions and doing 1,000 problems to understand this definition. So I compute the flux integral. So basically the flux integral is f double m ds. And the vector field, of course, is given in any problem is x squared, y. This is p, this is q, no? P is the first component, q is the second component. Both are scalar function. And the curve is also given as a circle. Where the center is in the origin and the radius 3. Forgive me the wrong sketch. It's in the origin, I promise. Okay? In the origin. This is x and this is y. And remember, I need to compute the flux. The identification is flux. And flux, we can. So one possibility is compute the normal unit vector, but no. I propose you always do it using that formula. P dy minus q dx. And remember, the most important is you finish any problem of the line integral converting this line integral and the single integral que we are doing in Calculus 1. So, and the integral que we are doing our life. Okay. Now, for doing this job, you need to do the parametrization. Sorry, this is important to see que the curve, the orientation in this direction. ¿No? Y I assume que the normal vector is in this direction. So basically, I want to find the flux to get out the surface. Remember, the other dimension get hiding is perpendicular to the whiteboard plane, and the value I suppose is 1. Okay, so now it's a classical parametrization. When you see circle, ellipse, something, the parametrization is obvious. Que es the radius get 3 cosine theta, no, cosine t. Could be theta, but no, I like t. And y is equal to 3 sine t. And this satisfies perfectly with this orientation. Suppose t equals 0 is this point, right? And t equal pi over 2 is this point, because in pi over 2 cosine is 0 and sine is 1. Entonces the point, that point, ¿no? Que es the point 0,3, and t equals 0 is 3,0, ¿no? Because cosine 0 is 1 and sine 0. Cool. Now I compute the derivative of this. In order to find dx and dy. Derivative cosine is minus sine, minus 3 sine t dt. Remember dt because you are finding differential, not derivative. Actually, I know that dx dt is minus 3 sine t. But in order to put an elegant way to get inside the line integral, you compute a differential. My formula somehow involving differential. Okay, just forget about that part. Okay, likewise, when you differentiate this, derivative sine cosine is 3 cosine t dt. Okay, cool. Now we are ready. So this line integral is converted to one elementary integral. I forgot the most important. The most important is the domain of t. But let me write here, no. The domain of t. So when you specification parametrization, you need to apport the domain of t, que is in between 0 and 2 pi. Because in another problem, I don't want the full circle. I want a quarter of the circle, entonces t is in between 0 and pi over 2. Pero no, in this problem is a full circle, but I need the specification. And this is the limit of t. Remember, we're doing a conversion. The line integral, completely new, weird for us, to the another integral that you know very well, calculus 1, calculus 2. Entonces, who is p? No, p is x squared. P is x squared. Look, this is p in the vector field, and it's a q in the vector field. Entonces, es x squared. But I want to write the integral using only t. Pero es que x is 3 cosine. Actually, is 3 cosine t squared is p. We are doing that part. dy, with dy. Dy is 3 cosine t dt minus q, que q is 3 sine t multiplication by dx is minus 3 sine t dt. Everyone follow me? Okay, now we have integral from 0 to pi. This is 27, no? This is 27. Welcome from 27. 3 squared is 9 times 3 is 27 cosine cubic t dt. Plus, because we have double minus, 9 sine squared t dt. As always, I want to skip that part because it's long, no big deal, calculus 2. The answer is MAC. And MAC represents the flux of this vector field on this surface is given. Cool, guys? Do you understand or no? Super or no? And always we are doing this way? No. Depending on the surface. Depending on the surface. I bring another example in which you don't need to convert to T. You are doing the natural parameterization. Depending on the problem. So I bring two more problems. It's different. So far, everyone follow? No. Answer me. But the chat, I activate the chat. The chat is working. You type if you want, or you activate the microphone and say, I don't understand anything, please explain me again one part, a specific part. Come on, come on. I'm waiting for you. Let me check out this. How many students we have today? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 students. Wow. Osvaldo, Álvaro, Sean, Ellen, Jan, Alejandro, Bernice, Lola, Tian Hao, and Ernest. Okay, wow. I don't know what happened. This subject is hard. It's not for everyone. I explained at the beginning, and you cannot afford to be absent in the lectures. Oh, you see in the YouTube, no? It's not the same. Okay, okay, true. What is true? Alejandro, what is true, Alejandro? Activate the microphone and explain. Do you understand very well this example?
Yeah, I understand. Yeah, I was agreeing with you about the whole attendance thing.
The last day, I don't care. The last day I compute the overall grade. So you have 50 something. I put F or D. I don't know. Okay. Entonces now example 2. Example 2 is a little bit different because it's the same idea, no, of the flux. But in this case, the vector field is given is y comma minus x. Okay, one more time. This guy is P is the first component, and the second component is Q. And the curve can somehow represent the surface. It's a line, it's a segment, it's a segment. It's a segment, one segment like that can go from 0, 0, to 1, 2, 1, 2, 2, 2. 2, 2. Okay, this is the curve. And the orientation, I suppose, is in this direction. This information is given. Who is given or you assume, according to your goal. Okay. Entonces, in this case, it's no circle. Entonces, no cosine, no sine. You assume the natural parameterization. I call this, it's in my language, natural. Natural is no parameterization. So you suppose que x is x. And y, well, y is no, y is y. But who is y in my curve? Now, this line is the line y equal x. Yes or no? Because the slope is 1 passing through the origin, to say y is x also. Now, dx is dx. And dy is also dx. It's a super easy example. I promise that after I could go a little bit more complicated. So the formula for finding flux integral is p dy minus q dx. And you convert to another integral. In this case, the independent variable I want to assume is x. So x go from 0 to 2. So you convert the line integral, complicated, in one easy integral. And how is p? P is y, but y is x. Look here. This is statement. And dx is dx. So dy is already dx. Minus. Minus what? Minus q. Pero q is minus x. Okay, cool. I like that because si es positive, I suppose que cancel out is 0, no flux. Okay? In this case, yes, we have flux. And dx is dx. Basically, the problem is reduced to this easy x dx plus x dx. Okay, it's twice. It's the same, combined, like term. Integral from 0 to 2 times x dx. 2 is a constant. Outside, your integration like a cal 1. Antiderivative, this guy is squared divided by 2. Evaluating between 0 and 2. And now cancel out that 2. And the answer is 2 squared, no? Minus 0 squared, 4. The answer is 4. I want to show you the next time I send to you one application in Geogebra. Okay, I want to somehow verify not all the problem, but the elementary problem. Okay, basically we are doing, no? For example, Flux Integral. Okay. Let me share the screen. Okay, there you go. This is, I don't know if you can open or not. I encourage you to try to open that. This application. Close this. Okay. Well, in this case, I have an example, but I want to modify for the example that we have. The example that we have, the vector field, the component R, Y. And do you see the application or no? Minus x. Cool. Minus x. Okay, now, look at that. This is the vector field. You click here to see the vector field. This vector field is rotational, so the curve is not zero. It's not conservative, of course. And this rotate clockwise. Okay, the curve is negative. Okay, but this is not a problem now. I don't care. I care flux. Okay, it's this integral. And the segment is 0, 0 to 2,2. Okay, and the answer is 4. Look, the answer is 4. And the normal vector is not in the direction que I suppose, in the opposite direction. One, okay, it doesn't matter. Si you change the normal vector, entonces the flux integral is not 4, it's negative 4. It's the only difference. But in this case, one mnemonic device to remember that is you travel in the same direction of the orientation of the curve. You walking on the curve, and you moving the right arm point to the right. That's the normal vector. Okay? Si es to the left, it's another normal vector, pero es the opposite direction, opposite orientation. It's the technical name. Cool? Do you understand or no? Do you understand or no? Guy, answer me. Answer me. Okay. Yeah. It's yeah. Ili. healing. Okay, erase the board. Yeah, we understand. Alejandro is a we, in plural. Okay. Okay, okay. I try to explain. I suppose que well. You let me know. Because the well or no well, on well, is completely relative. So you're true and my true, no necessary coincidence. Okay, cancel. Let me try to share the whiteboard. I want to bring one good example now. Okay, condensing everything we studied so far about the line integral. Okay. Example, I don't remember si es number 3, no? Number 3, I guess so. Number 3, no? Okay. We have example 3, no? It's 3. We have vector field, always is given. Don't be scared, the expression is more complicated or no. Y squared minus 4y plus 5, comma 2xy minus 4x minus 9. This is my vector field. I want to find everything. I want to find everything. I want to find circulation. Okay. I want to find flux. I want to find a potential function or no. I don't know if you have potential function or no. Everything that we studied so far. Okay, what's the problem? Simple. Right, professor, we cannot see the whiteboard. Okay. Try. Let me try. Don't worry. Let me try one more time to share. Switching. Whiteboard. Let me know if you see now or no. According to my computer, I suppose that you are C. Si no, I need to restart again. You see or no? Answer me. Yes or no? Okay. I can see. Okay, perfect. Sometimes happen that there are some delay. No? So now, let me try. Look. This vector field is given. It's given also the curve C. The curve C is, let me try. 1, 2, 3, 4, and 1 here. It's a segment. It's a segment. It's the segment que connects the origin to, so at that point is the point 4,1, and that point is 0,6. Yeah, I travel, but in this direction. Okay, this is giving. I want to perform the circulation, the integral, and the curve C gets this. Of the vector field gets this guy. Horrible. By the way, this guy P, and this guy Q. Dot product dr. Circulation first. I want to compute everything in this circulation, flux, both. Okay. So now I can use in this case the natural parametrization because the segment line. No? See a circle, semicircle, there's a cosine, sine. No. In this case, no. Entonces, this is equivalent pdx plus q dy. This is a formula for the line integral over the vector field circulation. P I have, and Q I have. Pero P and Q both depending of X and Y. So I need to state the connection in between X and Y according to the line. No? This line is easy. The equation for the line is super easy. It is X over 4, no? Because the slope is 1 over 4 and passing through the origin. Super cool. Now, I assume que, well, que dx is dx, because x is equal to x, is a natural parameterization. So basically, some people, I don't know why, call x equal t. It's possible, but no, it's totally unnecessary. So x is x, and because lie always parameterization t t t t. No, parameterization is any f. And dy es obvio. dy es obvio que es derivative de this, que es dx over 4, ¿no? Okay, so I have in my hand the connection between y and x, and the connection dx and dy like a function of dx. Okay, thus I go to this integral. I want to copy now using the parameterization que es x, and x go from 4 to 0 in opposite direction according to this. Don't be scared for this. You copy that. You see what is the starting point and what is the end point. You put it here, lower limited and the starting point, and upper limited. I put intentionally to illustrate that there are a lot of possibility, and the orientation is the orientation is given in the problem, and you respect this. And how is P? You know, P is this expression that involves basically Y, but I don't care because I know the connection. So I copy P. P is Y squared, but Y squared is Y is X, sorry, X over 4 squared, Y squared, this guy, minus 4, Y no, X over 4, X over 4 again, and plus 5. This is cute. I did our para list of the integral. Dx, and dx is dx. So everything multiplied by dx. Plus q. Who is q? Well, q is 2x and y, remember, is x over 4, no? Minus 4x minus 9 dy. But who is dy? dy is dx over 4. Okay? At least I set up this integral. The rest is algebra. Okay, I don't want to, but it's not important. I watch the time with the algebra, intermediate algebra, color algebra, calculus 1. No. And you evaluate that, and in the story, your integration, of course, and evaluation, and the answer is 1. Answer 1, wow. Answer 1. Unbelievable. I encourage you try to do after the class. If you want to, always I double checking my problem. You know that the answer is always good. Okay, cool. Now, what should I do now? One of professor, wait. Another student said, wait. I recommend strong. When you face this problem of the circulation, your computer, you verify if my vector field is conservative or not. Let me verify the conservative. And the fantastic way to verify the conservative is compute the curl of the vector field. What is the formula in 2 dimensions for the curl? It's easy. It's partial derivative q with respect to x minus partial derivative p with respect to y. When you differentiate q, is this guy, with respect to the x, it's obvious that we have 2y minus 4. Let me checking. Derivative x with respect to x is 1 to y, because you consider that y is constant, 2 is constant, and derivative with respect is negative. Cool. This part is this part. Minus p. Derivative P with respect to Y is 2Y again, minus 4, derivative phi is 0. Wow, this is 0. The curve is 0. That means that our vector field is conservative. Si es conservative, exists the potential function. And you compute the circulation line integral and the easy way. Not necessarily complicate your life too much. So you compute the potential function. The potential function, the name assigned for the potential function is phi. Phi x comma y. And this is super easy. Look, let me show you. You find the antigradient. What means antigradient? Antigradient means the antiderivative component by component. So you compute pdx. The first component, antiderivative with respect to x. It's doing. It's easy. Antiderivative of the expression p, que p is y squared minus 4y plus 5. This is p, right? Let me show you. I copy that. Yeah, I copy. And your integration with respect dx. It's obvious que es xy squared because this is considered constant and integration 1 with respect dx is x minus 4xy plus 5x. Okay, and you copy something here. This is x squared. And this, at least this is one part of the potential function. To complete the picture, we are doing the antiderivative again for the q part, but we respect the y. The antiderivative, what is q? Q is, let me come back to the beginning, is 2xy minus 4x minus 9, and you integration now with respect dy. Okay, cool. Entonces, you 2x is a constant, antiderivative y is y squared over 2. Entonces, the 2x cancel and stay xy squared minus 4xy minus antiderivative 9 is 9y. We are ready. We are ready to find the potential function. Potential function in any point of our vector field is the collection of the antiderivative. Entonces, the collection of the antiderivative is. Okay, there you go. The collection is the part gets repeated. Gets this and this. You take it, but only one time. And the part is not repeated. You take also. It's like an intersection, both expressions. Wow, this is my potential function. Because in the specific example, que es conservative field, vector field, que the potential function exists, I have in my hand, you can compute the circulation integral without integration. Is evaluate the potential function and the always end point minus initial or starting point. Who is the end point? Well, the end point is 0, 0. Look. And the starting point is the point, wow. The point 4,1. Just plug it in. Okay, plug it in where? In the potential function. Okay, and 0, 0. Es obvio que es 0, ¿no? Si everything is 0, entonces 0 minus something. When you evaluate 4, 1 here, well, we have 4, x is 4, look, x is 4, y is 1. Entonces 4, 1 squared minus 4 times 1 Plus 5 times 4 minus 9 times 1. Cool. This is 4. This is 16. This is 20. And this is 9. Okay, so we have, let me see, the positive guy is 24 and the negative guy is 25, and 24 minus 25 is negative 1, but don't forget this negative 1 that we have in the front, and double negative becomes positive. Wow, the first answer without do almost nothing. Determine si the vector field is conservative. Si the vector field is not conservative, entonces no. The only possibility to compute the circulation line integral is doing the line integral, not the resource of the potential function. Do you follow me? Do you follow me? Cool. Cool. Now, by curiosity, just curiosity, we are doing the flux integral in this vector field and the same curve. Okay? Okay, by the way, I suppose, using my common sense and my imagination, okay, the normal vector is in this direction, no? Okay, remember, how do you know that? When you travel along the curve, you put the right hand, right arm, and you're pointing to the right, is this, no? So normal vector is this, and tangent vector obviously is this. Is a T. It's the same. But I don't care. I don't care. See, I want, okay, so you apply the formula. The formula default imply, so the convention is using the normal vector in this direction. So you want in opposite direction, well, you compute this and change the sign, end the story. But no. I respect this convention, and you compute the flux integral, que es P dx minus Q dy. Dx. P dy, sorry, is the formula, minus Q dx. And the same curve. Okay, cool. You immediately convert the problem in one single integral with P. Well, P is here. P is this. Actually, I did before. P is y squared is 1x over 4 squared, que es y, minus 4x over 4 plus 5. And dy is dx over 4. It's the same, but in different formula. Minus q, and q is 2x multiplication x over 4 minus 4x minus 9. A multiplication by dx, dx is dx. And this integral go from 4 to 0, exactly the same. Algebra, combine like term, okay, antiderivative easy. The answer is minus 60.66. Actually, it's negative 182 divided by 3. So I encourage you, this problem gets a little bit more complicated. No? You try to verify in the application I sent last time. Okay, I sent to you the last lecture, the link to connect it to application in Geogebra. The first one is circulation, and the second is flux. The only thing you should do, same like I did before, you put P and Q to define the vector field. You move into this, define our. Basically, the application is limited because it's only a segment line or circle, or semicircle, or one specific classical figure, no? Not all the figure that you suppose. No, it's the complete universal, but that's a typical problem of this. And your verification, this number, and verification, why not the signs, and you understand a little bit more clear the physical meaning, no? Yes. Okay. Any question? Okay. What is my conception about calculus 3? I saw the lecture in the other university of the calculus 3, and the teacher spent a lot of time in useless part, algebra and calculus 1. This is easy for you, I suppose. My focus is to understand the meaning of the thinking we are computing, number one, and number two, the specific formulas that we're using to this. Okay? The rest, the algebra, unfortunately, the algebra and the calculus 1, it's a long part. You say now you are doing it this way, in my opinion, it's in my opinion. I discussed it with another teacher. So you spend maybe the 70% of the time doing the Cal 1 algebra. Okay, I respect that. Okay. Now, today, right now, we study fundamental theorem of calculus of the line integral. Wow, what the hell? It's acronic. Fundamental theorem of calculus specific en line integral. Bueno, you know fundamental theorem of calculus en Cal 1. I want to recall in Cal 1. And fundamental theorem of calculus contain two parts. However, the first part is the most important, is the integral from a to b of the derivative of one function. The only thing that you should do is compute the antiderivative, which obviously is the original, and evaluate in between a and b. So the answer is f and b minus f and a. End story. Fundamental theorem of calculus. Look like stupid, ridiculous. Easy, elementary, straightforward. But the same concept you apply in line integral. How? Suppose that you have the integral, line integral of the one vector field dr. Let's suppose that this vector field is conservative. This is the most important moment, conservative. Therefore, I can assume that this vector field comes from for the gradient of the one hypothetical potential function. And now when you apply the anti-gradient, you find the potential function, and the integral of this is potential function evaluate in the endpoint minus potential function in the initial start point. Guys, do you see the connection in between this and this? In my opinion, okay, gradient look like similar to derivative. But you know the gradient is derivative, pero en any component, it's a vector. The only thing that changed in between this statement and this statement, Cal 1 and Cal 3, is that Cal 3 talking about 2 dimensions or 3 dimensions, and Cal 1 talking about 1 dimension. It's the same. It's the same. Now, si you understand very well this, si es no conservative, no. Pero es obvio que si es en el Cal 1, si this is not the derivative, we cannot affirm this. Okay. Entonces now, one important conclusion que I take this. Suppose now if we have that situation. No record. Suppose que we have integral. Pero enclosed. Okay, you are familiar with this. What it means that? That means that our curve is closed. Okay, close of the vector field dr. And one more time, the vector field inside is conservative. And one more time, this vector field comes from for the gradient of the one hypothetical potential function. And es obvio que dice zero. Why es zero, professor? Because it's a closed curve. You take any point, and you suppose que this point is both is n and star. And you rotate, it doesn't matter. Entonces es zero, it's over, right? So si you have a conservative field, any closed curve, can you compare the circulation integral is zero. But the most important is this is path independent. Path independent. What means that? Suppose you have 2 points, P1, P2. E is conservative, of course. Suppose hypothetical trajectory here in this direction. And hypothetical trajectory here in this direction. I know that the integral in this consider both S0. That means if you change the direction of this integral and this integral is the same value but opposite sign. Therefore, that means that the circulation integral, when you have conservative field, is path independent. What means that? I don't care the path. I only care the starting point and the end point. Any trajectory, the value is the same. Unbelievable, but it's true. Okay? Okay? So I propose you doing 2 problems of the fundamental Theorem of Calculus in line integral. One in 2D and one in 3D. Do you understand the theoretical idea or no? Guys, this week is super important. This week I try to cover everything. Now I try. Now the next week we are doing the review. And the rest of the time, see, we are doing a special topic. I don't know, it's totally optional. Example 1 of the fundamental Theorem of Calculus. Suppose vector field is given is 4x squared plus 8xy, comma 3y squared plus 4x squared. And I need to compute the circulation integral of this vector field along. Entonces, look, it's weird, and this is a clue to understand this kind of problem, no? It's given 2 points, the point 0, 0, and the point 1, 1. You see some problem similar to this in the review package. And the trajectory in between this point is completely crazy, like that. It doesn't mean it's path independent, because you have no equation for this trajectory. So just in case, I checking see my vector field is conservative or not. Si it's conservative, you find the potential function and compute the potential function in between 2 points, and that's it. Okay, let's do it. The formula for the curve in 2 dimensions is qx minus py. This expression is p. This expression is q. Okay, derivative q with respect the x is ax, no? Derivative, partial derivative q with respect to x, this is a constant, it's gone. This is ax. Cool. And partial derivative p with respect to y. With respect to y, this is constant is gone, and it's ax. Wow, it's 0. See the curve 0. We prove done, yeah, que our vector field is conservative, and you find the potential function. And the potential function is super easy. Look at that. The formula is antiderivative p dx. Antiderivative 4x squared plus 8xy with respect to x. Antiderivative is. Entonces antiderivative es 4/3 x cubed plus 4x squared y. Okay, so plus 1 divided by 3 plus 1 divided by 2 and 8 divided by 2 is 4. Likewise, potential function and the other component is antiderivative q dy. Who is q? Q is 3y squared plus 4x squared dy. And the answer is y cubed plus 1 divided by 3 and 4x squared y. Okay, so my potential function is always the collection any expression that appears in the antiderivative. That is the antigradient. And you take everything together. That's 4 over 3 x cubed plus y cubed plus, in this case, this is repeated. You take one time. This is my potential function. Cool. Super easy. Now evaluate. You want to compute this circulation integral. No, not doing anything. Evaluate at the point. What is the starting point? What is the end point? I suppose that the direction is in that direction. From 0 is the start point, and this is the end point. Ok, entonces sí, es evaluate phi en 1,1 minus phi en 0, 0. En 0, 0 es obvio que es 0. En 1, 1, no. You plug it in 1, 1, 1, 1, 1, and the answer is 19 over 3. Boom. Kindergarten arithmetic. Any question? Everyone follow me? Fundamental theorem of calculus for a line integral. It's more general concept you see in Cal 1. Let's do another problem, but in 3 dimensions. Okay, answer me something. I do well. You understand? You follow me? It's crazy? It's complicated? It's understandable? It's the most important. No, the question is easy or hard. I know the answer. But it's understandable or is crazy? Suppose one vector field in 3 dimensions, 2xy plus c cosine x, comma. This vector field contains, of course, 3 variables. It's a vector field x, y, z. It's a classical 3D, no? 3 components. The comma is a comma, x squared plus e to the c, wow, weird. Minus sine y, comma, y e to the c plus 3c squared plus sine x. Wow, weird. Don't be scared. Don't be scared. The first job is compute the curve of this vector field. Remember, in 3D, the curve is a vector, no scalar function. The another notation that we studied, remember, was del cross product f. Either way, the way that you prefer. So ese cross product is I, J, K, no? And del is the symbolic partial derivative. And you put PQR. It's a P. It's a Q. And it's a R. PQR. You copy if you want, no? It's 2xy plus c cosine x. This is x squared plus e to the c minus sine y. And finally is y e to the c plus 3c squared plus sine x. Okay, look like long, but no. And remember, my recommendation is copy I minus j and k. You know, you're familiar with this. Okay, there you go. For the first one, case I, you delete mentally this and this. You differentiate this with respect the y, que es obvio que es e to the c, no? This is a positive, minus, and differentiate this with respect to c, que es e to the c. Wow, it's zero. It's zero. Do you see? Okay, let me use another color now. Suppose green color for the j. Okay, suppose now I delete this and that. And you differentiate with respect to x. The only trigonometric function is sine. Entonces derivative sine es cosine. Cosine x. Minus, and this derivative this with respect to c es el cosine es constant. Entonces derivative de c with respect to c es 1 es cosine. Wow, cosine. Es 0j. Let me use in blue color maybe. The k part is the part and this part. Derivative this with respect to x is 2x. And derivative this with respect to y is 2x. It's 2x. It's 0k. Conclusion. Our vector field is conservative because the curve is a zero vector. Okay, the vector 0, 0, 0. Okay, cool. Now the easy part. Compute the potential function. The potential function is the anti-gradient in 3 dimensions. Yx, alphabetic order. Yz. You compute the antiderivative p with respect to x. It's doing. You compute the antiderivative q with respect to y. And you compute the antiderivative r with respect to c. It's doing. Okay. You take that guy, put inside here, and compute the antiderivative. Super easy. With respect to x is x squared y, like so. And well, the cosine part, antiderivative cosine is sine positive, no? Plus c sine x. Makes sense? Do you follow me? So you forgot p, you forgot q and r. No, you focus on p only. And antiderivative p with respect to x. Okay. Now you focus on q. Antiderivative q with respect to y. Okay. Entonces now, si you antiderivative q with respect to y, well, entonces x squared consider la que consta, ¿no? Pero es y. Exponential es c, pero y. And sine is cosine. Because the derivative sine is minus cosine, but we have minus in the front, become positive. Cosine y, no? Cool. And finally, r. And your antiderivative with respect to z. The antiderivative with respect to c is, and the first one is y e to the c. Remember, antiderivative exponential is the same function, that's e to the c. Plus, this is c cubic divided by 3 is c cubic. Plus, and the derivative sine, pero es con respecto de z. Entonces, c sine. C sine. And finish. Anti-gradient, que es antiderivative component by component. So what is my famous potential function? What is my famous potential function? Well, my famous potential function is the collection every expression. In this case, x squared y, I take one time, it's repeated here, but I don't care, plus exponential cy is this and this, you take one time, plus c sine x, I see is repeated also, but I take one time, plus cosine y, not repeated, take this and c. Okay. This is my potential function. So my problem is evaluate. I forgot to say that I forgot to say again the curve. But the curve is similar. But the curve is in 3D. Wow, wait. The curve is in 3D. In 3D, not in 2D. So suppose we are doing the 3D environment. X, Y, and Z. And my curve is completely crazy, arbitrary curve, and between the origin is 0, 0, 0, and the point 1, 1, 1. Okay, this point 1, 1, 1. I don't care the curve because it's path independent, because it's conservative field, because I compute the curve is 0, and that part is super important, the most important. Now the rest is evaluate the potential function at the point in the story. Evaluate phi 1, 1, 1 minus phi, 0, 0, 0. Well, I copy in my piece of paper after evaluate, simplification, the answer is 1 plus c plus sine 1 watt, 1 radian, I guess so, and cosine 1 at the finals. Do you understand or not? Guys, answer me. Do you understand or not? Well, it's super complicated. Everyone follow me? Okay, no, the time is over, no? Diego Logo left, okay. Answer me, say something. Professor, we are lost. Come on. Bueno, no opinion, okay. I am good. Okay, Alejandro is I am good. The rest, Alejandro is I am good. And it's a little confusing, but I will go to recording. Okay, and also remember, I explained the first day. You can ask me anytime. You email me, Professor, I don't understand that part. Don't problem. I try to explain. I have scheduled as a tutor que explain que es Tuesday in the morning and Friday in the morning. Okay. So now you can reach me. Okay. The problem is que si you have bad grade, I put the D or F in the overall grade. Okay. Entonces, okay, guys. We continue Wednesday. This is important week. This week. And stay here one moment. I want to drink some water. I run back. Okay. Ernest, you hear me or not? Ernest. Okay. Se fue. N. N. Do you hear me, N? Okay. I want to know what is your your goal, because you are doing nothing. Okay. I see. Do you see the blackboard? No. Your grade. What is your plan? What is your plan? Your plan is to stay or drop the class. I can help, but you need to send me the test. So, test number 1. So you let me check it in my spreadsheet Excel. Your okay. See, I am wrong. You let me know. No? N. Charlie N. Taylor. You don't do anything online in the test 1. Okay. You don't, and the test and the written test you get 76. I want to stay, but I have been working 2 jobs. Okay, it's not my problem. Okay, you have it's not my problem. You have 3 part-time job, 5 children. This is not the problem. The problem is understand, doing your assignment well. Entonces, this is not the good time for you. You need to make a decision. You stay and you continue in the same situation. I guarantee you that you have D or F in the class. So you, but currently I have COVID. Oh, okay, no, okay, I understand. One possibility is you thinking the best way for you. I am no enemy. I am friend. I try to help. So you consider, okay, and this is you lost too much time. Why don't you drop the class and you take another teacher in another semester? So you consider you have possibility to continue. I give you opportunity, like you send me the test 1, but communicate with me by email, not necessarily now. Thinking the best way I can help. Okay. You communicate your decision. No, professor, I am drop. Okay. Or if you want, I drop for you. I don't know exactly the mechanism in the Miami-Dade is good for you. See, I drop or we drop by yourself. The best way. So you decide continue. So say you need to. We create a plan, a schedule to fix it. But this is hard. I know it's hard because this hard subject hard. Si es call algebra, you can do that. But calculus 3 is super hard. So it's, I don't know. It's up to you. Okay. Okay, Ernest. Okay. Thinking and let me know. Cool. Bye. You want to say something more or no? Okay? Okay.